Hello, everyone. My name is Zachary Hartman, and I am a predoctoral student at Lowell Observatory. And this just means I am part of a graduate program at Georgia State University, but I am finishing my research and degree at Lowell Observatory, working with Dr. Gerard Van Bell on some interesting stuff that I'll get to later in this talk. So the title of my talk is Bowling for Turkeys, Searching for Triples, Quadruples, and More in Wide Binary Systems. And on the left over here, you can see an example of a young wide binary system. So in the middle there, you have two stars that form a close binary. Their separation is about 20 astronomical units, or AUs. And astronomical unit is just the distance between the Earth and the Sun. And then you have a wider component, this what appears to be brighter star, but is probably just due to the dust that is around there, forming a wide pair that is about 200 AU. So just to put things into perspective, the solar system, the distance from the sun to Pluto is about 40 AU. So this other wider component is very far outside of what we would consider our own solar system, if we happen to live in that system. So just a little brief overview of my talk. So I'll go into an introduction about what wide binary systems are, go into a brief simple discussion of the method we used, and then I will talk about the catalog that we created, which is called SuperWide. And then we'll go bowling for some triples. So in this picture on the right, this is a picture of the sky in the southern hemisphere. And in this picture is a wide binary. Now, you may think it's these two bright stars that are right in the center of this picture. But how do you know? So there are a couple of ways we can figure it out. One way is by looking at the angular separation, how far apart they are on the sky. And these are relatively close to each other. The second method we could add on to that is using proper motions, which is the motion of the star across the sky relative to us. And for these wide systems that we're talking about, we want these to be nearly identical for reasons which I'll get into later. And another method is using radial velocities. So how quickly a star is moving away or towards us. We also want those to be relatively similar to each other if they're going to be a binary pair. And then we also have distances, and what astronomers use for that is something called parallax. And from the parallaxes, we can get the distances. And if we take the distances of these two stars, the one on the left is roughly 4 light years away, and the one on the right is roughly 400 light years away. So those are pretty much not a pair. But there is a star that is in this picture, and that is the little red circle that the red arrow is pointing to now. And that is Proxima Centauri. So the bright star on the left is Alpha Centauri, and Alpha and Proxima form a triple system. Their angular separation is about 2.2 degrees. And just for reference, the moon is about half a degree. On the sky, physical separation between those two is about 13,000 astronomical units, so very much farther than what we were talking about with that young triple system at the beginning. And in the field, about 30 to 50% of stars are binaries, and these are any type of binary, close, wide, but specifically for the wide, about 2% are wide binaries. And what do I mean by wide binary? These are binaries that have separations greater than 10,000 AU. So if you look at this plot on the right here, this is from a study that looked at nearby solar type stars and looked at the distribution of binaries. So this is a pretty complicated plot, but let me walk you through it. So this is just a histogram. So the y-axis represents number of stars in each bin. On the top, you have the physical separation in log space. So each one of those numbers represents 10 to the x. And then on the bottom, same thing, but for the period in days. So for this wide section over on the right here, you have greater than 10 to the 4, so greater than 4 in log A. And then the period of these systems are 10 to the 10 days. Now, on the other end of that, you have close binaries, which have periods of could be a day, could be less. So for these wide systems, I mentioned before that we consider the orbital, that when we look at the proper motions of these systems, we can want them to be as close as possible because they're moving on the sky at the same rate, in the same direction. And this is because the orbital motions in these pairs are basically non-existent. They are so widely separated that you couldn't really detect. I mean, the periods of these systems is 10 to 10 days. We will never see these systems orbit in our lifetimes. Um, Now, for the purpose of this talk, all identified pairs that that I consider to have high probabilities are to be considered binaries. Um, if you have a pair that has a 95% chance, there's still a 5% chance, but we're relatively very certain that they're a binary. Now, one interesting fact for these wide binaries is I'm saying that they have separations greater than 10 to the 4 astronomical units. Now, the typical protostellar core size, so the clump of gas that eventually contracts down to form stars, is around 20,000 AU. So this means these wide binaries are larger than the typical core size. And this plays a part in we don't really know how they're formed. We'll get into that later. So now wide binaries are very important to other parts of astronomy. Now, these systems are essentially single stars with different masses, but with the same age and chemical composition. And what this means is, in particular, you can look at metallicities of these wide binaries. Now, metallicity is simply the proportion of material in a star that is something that is other than hydrogen or helium. So if you have a solar type star, and then you pair it with a star that is relatively faint and is very difficult to get a spectra of and therefore get the metallicity of, then you can use the metallicity that you can derive from the higher mass star to get the metallicity or to infer the metallicity of the lower mass star. The other reason these are important is because they are weakly bound to each other. So if these two stars happen to pass by another star, then it could rip the binary apart. If it passes by a giant molecular cloud or a black hole, these could also rip apart these wide binaries. So they're important to the galactic dynamics and studying the galactic environments around the galaxy. But another area that this plays into is dark matter. One of the ideas of what makes up dark matter is the idea of machos, so massive compact halo objects. And the idea is if these existed and they had different masses, they should change what the separation distribution of these wide binaries looks like. And so this plot on the right shows this for different masses of perturbers. So the circles represent 1,000 solar masses. That's what the M with the little circle and dot in the lower right stands for on this plot. The triangles are 100 solar masses, and the squares are 10. And so you can see that for the 10 solar mass distribution, it has a lot more wide binaries versus the 1,000 mass one, which really cuts down on that number. So I mentioned this kind of previously, but we don't really know how they're formed. That's kind of the drive behind what my research has been, is trying to figure out, okay, what scenario most aptly describes how these systems form. Now, there have been many proposed. I'll go through a couple of them. For one, the cluster dilution method. If you have an open cluster and as it's dissolving, you have interactions between a group of stars that may leave a couple of them bound to each other. The unfolding of triple systems, we kind of saw this. You saw this as a young system in the plot on the right that I showed at the beginning. And the basic idea behind this is as this system evolves, the stars interact with each other, and that interaction can lead to the inner binary becoming closer and the outer component getting thrown further out. And then you have this idea of adjacent cores, where you have two protostellar cores in the same star-forming region, forming stars at the same time, and through gas friction or interactions with other stars nearby, they become bound to each other. And so our search has really been to try and figure out whether or not these different proposed scenarios could be true. So how are they found? We use large databases. So this is a very statistical area of astronomy where we need large databases in order to characterize chance alignments. And chance alignments are basically pairs that are on the sky. They appear to be close to a star, but they aren't, they are not a wide binary. So as I was mentioning earlier, we have several ways of looking for these pairs. So number one, probably the most important thing that you need is angular separations, because you don't want a star that's on one side of the sky, and then on the other side of the sky, you saying that's a wide binary, because most likely it is not. So you need angular separations. The closer a star is to another star, the higher the chances are that it's actually a bound pair. And then with those angular separations, you put them in combination with a bunch of different attributes of stars. So proper motions, as I mentioned, the motion of the star across the sky, distances to that star, radial velocities. So as an example of that, if you look at the picture on the right, you have a couple stars in this frame. And if you were just using angular separations, you may say that this star, that the left star with the little star next to it, that may be a binary pair. And with angular separations, you don't know whether it is or not. But let's add proper motions into it. And so if we take a image that was taken at a different time and blink the two together, we get something that looks like this. And so you can see that the one star, the brighter star that I indicated before, is now moving, but the little star that was right next to it isn't. And then you have another star further away that is moving. So these two stars form what we call a common proper motion pair, or another name for a wide binary. And this other star, the smaller star that I was pointing to earlier, that forms a chance alignment, a star that is contaminating our sample. And so our entire method is that we basically want to figure out how to determine which pairs are chance alignments and which pairs are real pairs. And to do that, we need a large data set. And so we turn to Gaia. Now, Gaia is a great tool for stellar astronomy. And what it is a satellite that is in orbit around Earth. It is taking astrometric data on over 1 billion stars. Astrometric data includes positions, proper motions, and distances, or what it measures is the parallax, and then we can derive the distances from that. And so this was set up by the European Space Agency, and just recently the second data release came out. And so what we did was we took stars with proper motions greater than 40 million arc seconds. So these are stars that are moving relatively quickly on the sky relative to us. This came out to be about 5.2 million stars. And what we did was we used angular separations, proper motion differences, and the differences in the distance between the different stars in our catalog to figure out which pairs were most likely to be real gravitationally bound binaries. And I'm going to walk you through how we did the angular separations portion. So if we go back to that picture that we saw before the blinking, which is now on the right, I've drawn several lines. So the purple magenta line shows the angular separation between the true wide binary system. And then the teal lines represent angular separation lines between different chance alignments, stars that are contaminating our sample. So the goal is we want to recover our real pair and find a way to eliminate the chance alignments. And so if we go through our catalog and we match the stars that could possibly be matched to each other, we get a plot that looks like the plot on the left. And so in the lower left here, you can see that there is a small peak. that represents the population of real pairs in our sample. And then as you get to higher and higher separations, you start to become dominated by these chance alignments, which is the steadily rising distribution that you see going to the right on the plot. But you can see that even that these chance alignments even affect the pairs that are at lower separations that we think contain that where we think the real pairs are. And as you see on the plot or on the picture to the right, you have this really small separation chance alignment that if you didn't have proper motions, you think, oh, that's a real pair. Um, and so the way we figure out which ones are true pairs and which ones are chance alignments is we construct uh, another catalog, basically, where we take our star, shift it to a different part of the sky, and compare it to other stars in that area. And what this does is it essentially gets rid of the real binaries. So this is step one, figuring out just looking at the distribution in general. Step two is getting rid of those real binaries. So as you can see in the lower left now, there is no real binary population. This is a distribution entirely made of chance alignments. This is the shifted randomized catalog. And then step three is essentially to profit from doing that and get the real pair distribution out. So we take that chance alignment distribution that we fit previously, subtract it from the distribution that had the real pairs, and we get the real pair distribution out. And so in the end, we have two models. We have the chance alignments and we have the reals. And what we do is we do this again for the proper motion differences, and we do it for the distance differences. And from those models, we calculate a probability that these stars are actually gravitationally bound systems. And so with that, I'd like to present the super wide catalog. This is a catalog with 99,000 pairs with probabilities greater than 95%. The plot on the right shows the all sky distribution in right ascension and declination. The angular separations for my pairs range from 2 arc seconds up to 1800 arc seconds, and 1800 arc seconds is the equivalent of half a degree on the sky. Distances for my pairs can go beyond 500 parsecs. Physical separations out to roughly a few 100,000 AU. And this is all in a paper if you want to look that up. Now let's dive into the catalog a little bit. So here's the HR, or Hertzsprung-Russell, diagram of the primary stars in my catalog. And so what this diagram shows is a relationship between the star's luminosity and temperature. And it shows there's several features that I want to point out. So this body of this diagram is where main sequence stars reside. Up here in this kind of locus up here is where sun-like stars reside. Up here are red giants, and then down here are the white dwarfs. Now, for this plot, we use absolute magnitude, which is the brightness of the star at 10 parsecs, for the star's luminosity, and we use the color as a proxy for the temperature. And the color is simply the difference in brightness of a star when observed in different filters. So you can take this as, so Gaia B is a filter, and then Gaia R is a filter. The star was observed in both, and then the color is just the difference between the two. The secondaries look kind of the same, although there's not a lot of stars up here anymore. And the reason for that is that as you go down on this main sequence, the mass of your star decreases. So up here, around 0.8 on the x-axis, kind of where my cursor is, that is where the sun would reside, so solar mass stars would reside there. And as you go down the main sequence, you get the lower and lower mass stars. And now, so you may have noticed that in this middle area here, there's a lot more stars here than there were previously. We believe that these are mainly due to bad Gaia colors. So now I'm going to talk about the search that I'm doing. So this, going to a bowling lane and searching for turkeys. So we've already hit one strike because we found a star. we had 2 strikes when we found a wide binary pair, and now we're searching for that 3rd strike to get the turkey and finding close companions to these wide binaries. Um, so this is important to knowing about the formation mechanism for these pairs. So if we know how many triples, quadruples, and more there are versus the number of actual true wide binaries, which is known as the higher order multiplicity fraction, this could allow us to differentiate between the different mechanisms. Based on previous studies, this is expected to be high, about 70%. But knowing what the actual fraction is could be critical to figuring out which mechanism is the dominant one. You could use the separation of close binaries as well in these systems. If, for example, the unfolding of triple systems is the dominant mechanism, then you would expect the separation of the close binaries to be much shorter than what the average fraction in the field for binaries are. One of the interesting things about these triple systems is that most close binaries, so these are those binaries with periods of day, around that, they've been found to have a wide companion. So essentially, we're flipping this kind of the other way. So we're basically saying now, okay, we have these wide companions. How many of these have close binaries? How many of these have these inner subsystems that they're triples or quadruples? And another question we're probing is, how does this fraction differ across populations? How does this fraction differ between really, really old stars and relatively young ones? So that's something else we're looking into. But our search for triples begins with looking at the over-luminous components in the HR diagram. So this is now zoomed in onto a region in the HR diagram, specifically where K-dwarf stars reside. And you can kind of see it from this, and you could kind of see it in the other one, but there appear to be 2 main sequences. There's this one that is more heavily populated down below this yellow line. And then there's this other group that's above the yellow line that is less, that is sparsely populated. And so the difference between them is that one of them is the single star main sequence. That's this area down below the yellow line. But the other one could be a number of possibilities. So it could be that young stars are there. However, one of the side effects of us using a high proper motion sample for our study is that it consists of mostly old nearby stars. And so what this does is it essentially gets rid of the young stars. So we don't really think it's that. Another possible reason, the one that we're hoping, is that most of these overluminous stars represent possible unresolved binaries. So Gaia being as great as it is, it still can't resolve every star on the sky. And so if you have a close binary, Gaia may not be able to resolve it. But what would happen is that you get more light into the camera from the fact that you have 2 stars there instead of 1. And so what we've done is we've basically gone for each of our wide binaries and said, all right, let's determine an over-luminosity factor for each component in the wide binary. And what this is it's simply the absolute magnitude of the component minus the dividing line. So I have 3 examples that I'm going to go through. So one of them is this yellow line right here. This represents a not high metallicity, but not low metallicity pair. And the over-luminosity factor is then whatever this absolute magnitude is minus the dividing line. So if you have a positive over-luminosity factor, then you will not be considered over-luminous. If you have a negative one, then you will be over-luminous. Then for the other 2 stars you have, or the other 2 pairs that I'm examining, you have this lower metallicity pair that is shown in red, and then you have an orange pair that shows one component being not underluminous, but kind of the I don't kind of the right kind of luminous to be a single star, and then you have an overluminous star over here. And so if we plot the two components versus each other, you get something that looks kind of like this. And so the stars show the location of where those pairs would that I was examining as my examples would show up on this diagram. So the yellow star would appear kind of up here. The lower metallicity star would be down here, and then the star or the component or the pair that had the overluminous component would appear in this region here. And so when we were first looking at this, my group, we noticed a couple things. So number one, this kind of thing looks like a body. And then you have kind of an over density here and here, and those kind of looks like claws. So we decided to call it the lobster diagram. And so I'm just going to highlight 3 areas of interest. So you have the body of the lobster right here, where the overluminosities of the components are correlated, and they're true wide binaries. So these stars are 2 single stars that do not have that are not in a triple system. You then have the 2 pincer areas where one component is overluminous and therefore a possible unresolved binary, and then the wide binary pair is considered a triple system. Below the body of the lobster is where the primary component is overluminous, and to the left is where the secondary component is. And then down in the lower left region, you have the food for the lobster, where both components are overluminous, and that's where possible quadruple systems could reside. And so this is, and if confirmed, this could be a great tool for figuring out which systems to target for follow-up surveys looking for these triple systems. And so one of the things that we've done is we've looked into exoplanet surveys that look at light curves, or that take light curves, and looked for eclipsing binaries. So we looked in Kepler, we looked in K2, and we looked in TESS. And I'm going to highlight TESS because it is an ongoing project. So TESS is looking at the entire sky in chunks. There are 12,000 pairs in the superwide catalog that are in the TESS input catalog, so they will be getting observed sometime. And we already have some eclipsing binaries, and that's what I'd like to show you right now. So if we look at, so the plot on the left is just the lobster diagram with the eclipsing binaries that we found overlaid in different colors representing the components that have light curves. So some of them have only one of the components having light curves, others have both, and some are close enough where TESS cannot distinguish between the two, so they're both on the same pixel, and therefore we don't know whether the light curve is from the primary or the secondary. But this is from a primary star, and is specifically one that is over here, as shown by the line, and it is an eclipsing binary. So we're pretty happy about finding that one. Here's the phase light curve for it. And then we have this system down here, which is a contact, which one of the components is a contact binary, which just simply, and this is the phase light curve, so a contact binary is where the two components, or where the components that are in the closed binary it's actually the stars are close enough where they are touching each other, and it forms a kind of dumbbell shape. So this is what I've been doing with statistical stuff and looking through TESS. The reason I came out to Lowell Observatory is to work on Speckle Imaging. Now, Speckle Imaging is great for examining possible unresolved pairs and trying to figure out whether there is an actual binary there. So let me walk you through a little bit of that. So speckle imaging is where you take really short exposures of a target. So the plot or the movie on the left, let's see if it will play. This shows speckle frames being taken. And so you take 40 millisecond or 60 millisecond. These are 60 millisecond exposures. And let me just play it again. Where you're basically, so these 60 millisecond exposures kind of freeze the atmosphere when you take the data. And so what we do with that data is we take all these speckle frames. So there's normally 1,000 frames in a speckle data cube, and we take multiple cubes of data, and we basically take them and we run Fourier transforms on them. And so if you just use, say, a single frame or maybe one data cube, you don't get as much information unless you use all of them. So once you start to use all of them, so right now, let's say you were taking this image on the right is the resulting reconstruction of one data cube or one frame. And then as you add more and more to the analysis, you start to see, oh, there's a pair right there. And so this is how we are working with speckle imaging to resolve these pairs. We're taking the images, we're taking these short frame images, and then we are going and using Fourier transforms to reconstruct the image. And thank you to Nick Scott for providing those videos. So now at Lowell, we are building a new speckle instrument, actually. So this is QUIZY on the right. On the left is the LDT, which is the telescope that QUIZY will be going on. And QUIZY has 6 wavelengths in it, 2 near IR and 4 visible. But one of the more compelling aspects of it is that it has a wavefront sensor attached to it, which will allow us to characterize the atmosphere a lot better than what we are capable of doing right now with the current instrument setup that we have. And with basically knowing what the atmosphere is doing will allow us to take the atmosphere, not wholly out, but most of the way out of the picture, and allow us to reconstruct images better in the data analysis side. And so that's going to conclude my talk. So just in conclusion, there are approximately 99,000 high probability pairs in the high proper motion Gaia DR2 sample. We're looking at how do the widest systems form, but there are many more statistical methods that I didn't even talk about that could be used to examine this. Eccentricity was one of them, and metallicity and over-luminous M dwarfs are another. And I think that's time. And any questions? So it seems we have a question from Jim Davies. What does the time difference in pictures need to be to determine the proper motion? It depends. It depends on how large the proper motion is. So I can't really give you a definite answer on that. Sorry. It really depends on how large the proper motion is. For example, if you have a really slow moving star, you probably need to wait a while. But if you have a really fast moving star, it wouldn't be that long. Um, so one of the actually, so I forgot to mention that uh, I think tomorrow we are putting Quizzy onto a 1 meter telescope. So hopefully Quizzy will be up and running at LDT um, in the very near future. So uh, before the coronavirus crisis hit, it was a day away. So now we're getting it onto a telescope possibly, and it's going to be great. Um, so yeah, I'd like to thank everybody for your time, and uh, thanks again for listening to my talk.